Hello, welcome to Limits and Continuity. This is section 10.2 here at UTEP. It might be a different section if you're using a different book in other places. But as we saw in a couple of graphs from the limits numerically and graphically, graphs could have different behaviors on either side of the value we're trying to learn about with the limit. And we talked a little bit about the limit from the left and the limit from the right, but I'm going to put a definition in here just to make sure, now that we've used it a little bit, we understand what's going on. On a number line, any number line, in general, negative values are to the left and the positive values are to the right. For this reason, we write the limit as x approaches a from the left of f of x. Right? So x approaches a from the left, the limit as this happens of f of x. The raised negative sign after the a indicates that we're only considering values to the left. Similarly, there's a little plus sign here. We could define the limit as x approaches a from the right of f of x. I may refer to below, that's going to be left of, and above, always in reference to the number line. Above and below, a lower limit and an upper limit. Those types of things. Not lower limit, upper limit, but that's a calculator term if you're looking for some of this. When we say a limit exists, we're saying that the limit from the right and the limit from the left are equal. Okay? So this, all things that we've talked about in the first section of chapter 10. Okay. Now, let f be a function and let a be a number in the domain of f. Then f is continuous at a, so continuous is what we're defining here, if the limit as x approaches a of f of x exists, and the limit as x approaches a of f of x is equal to the function value. All right, so we could kind of make it three parts. If the limit exists, the function value exists, and they're equal. All right, so how can it fail? Well, it could fail one of those three things. The function f is said to be continuous on its domain if it is continuous at each point in its domain. If f is not continuous at a particular a, we say that it is discontinuous at a, or that f has a discontinuity. Thus, a discontinuity can occur at x equals a if either the limit does not exist, like in example 1, limit from the right and the limit from the left are different, or a discontinuity can occur, I forgot where it was, the limit does not exist, or the limit exists but the function value doesn't, or the limit exists, everything's good, and the function value exists, but they're not equal. All right, so no limit, no function value, or the limit is not equal to the function value. Three ways we could have a discontinuity. In general, there are three types of removable discontinuity. Three types of discontinuities. One is removable. Second one is a jump. There's just nothing we could do, and the third one is infinite. All right, so an infinite discontinuity, a jump, there's no way we could bring these together, but we can find a way with removable. What we're going to try to do is define a specifically so that we fill that hole. Not define a, define f of a specifically so we fill that hole. All right, let's look at some examples. Some functions are not defined at x equals a, but through the use of limits, we can find a suitable definition in order to make them continuous. These functions are said to have a removable singularity at a. If we're unable to fix the discontinuity, it has an essential singularity there. All right, it's essential. There's nothing we can do. So in these examples, we're going to find an appropriate value, if one exists, to make f continuous at x equals a. Our function is x squared plus 3x plus 2 all over x plus 1. And we want the a value of negative 1. So first thing we're going to do, and I'll tell you more about this in the next section, but let's substitute. Put negative 1 in for x. Negative 1 squared is 1. 1 plus 2 makes 3. 3 times negative 1 is a negative 3, so that's a 0 in the numerator, 0 in the denominator. And anytime we get 0 over 0, it tells us we got more work. That's it. That's all it means. 0 over 0, I saw a question on Reddit the other day. What is 0 divided by 0? It's anything you want it to be. All right, we can make it happen. we have to use algebra to figure out what this particular 0 over 0 is equal to. So we take our function x squared plus 3x plus 2 in the numerator divided by x plus 1, and we factor our numerator. X squared plus 3x plus 2 factors into x times x, 2 times 1, and 2 plus 1 will give us the 3x. Notice here, the x plus 1s will cancel out. And what we get is actually approximately x plus 2. This is a related function. And what that means is f of x behaves just like the function x plus 2, except at a equals negative 1. So this is the function that we're looking at, but using algebraic simplification, we could find a related function. And if we look at this simplified function here, and we put in negative 1 plus 2, we get 1. So if we define f of negative 1, which does not exist, to equal positive 1, what we're going to do is fill that hole like we did on that first example up here. With this definition, we're filling the hole in the graph, literally. Second example. F of x equals x squared minus 3x over x plus 4. We're going to use the a value of negative 4, and the first thing I'm always going to do is substitute. Negative 4 squared minus 3 times negative 4 over negative 4 plus 4. Negative 4 squared is 16. Negative 3 times negative 4 is a positive 12. 16 and 12 make 28. However, negative 4 plus 4 is 0. That's a 0 in the denominator. Anytime you have a 0 in the denominator, no, that can't happen. There's no magical algebra trick that can help us when only the denominator is 0. This tells us there's no way to make f continuous. There is an essential discontinuity. All right. Number 3. F of x is x minus 1 divided by x cubed minus 1. Our a value is 1. I'm always going to evaluate first. Put 1 in. 1 minus 1 is 0. 1 cubed is 1. 1 minus 1, more zeros. 0 over 0, nothing. Something can be done, right? A number over 0, no, we can't do that. If we have 0 over a number, that's okay to do. But if we have 0 over 0, more work to do. All right, so we have to do some work. So the first thing we always want to do is factor, if possible. And difference of cubes, you can look up the formula, factor difference of cubes. We notice again that the x minus 1s cancel out. Oh, that's our problem spot. That's cool. So this is our related function. These two functions behave exactly the same except at an x value of 1. It's the only thing that's different. If we evaluate the new function at 1, we'll get 1 over 1 squared plus 1 plus 1. That's 1/3. If we define f of 1 to be 1/3, then this whole function will be continuous. We just plug the hole. Continuity versus discontinuity. Remember, for continuity, you need 3 things. The limit, no, you only need 2 things. The limit has to exist and equal the function value that exists. Discontinuity, can we factor it away? Can we manipulate it away? We'll talk more about that in 10.3 with more examples. Thanks for listening.